Hello and welcome to the lecture. This week we move on to introduce and solve problems connected to projectile motion. To do this, we're going to need to understand how to work with vectors in 2 dimensions, which means we'll have to look at addition and subtraction of vectors. And through all of this, we're investigating the consequence of applying our kinematic equations in 2 dimensions. Projectile motion is an advanced application of freefall problems that we looked at in 1 dimension. When we think of projectile motion, we're looking at an object that is in free fall with 2 or 3 dimensions of freedom for its movement. In a 2-dimension problem, we'll see the object leave with an initial velocity, travel up and over, before reaching some max height and then beginning to travel down and over. In this lecture, we'll look at how to solve projectile motion problems, which means we'll have to think about some of the assumptions and the concepts that we will need to apply to make these solutions. Because our projectile has 2 degrees of freedom, that means vectors associated with the kinematics are more complex. If we watch that demonstration again, we can see that the velocity vector here in green is constantly changing. It starts with its greatest magnitude of velocity and constantly shrinks, but it's also changing direction the entire time. We notice that the velocity vector is up and to the right as it begins, and then after max height, where it's horizontal, it begins to turn down and to the right. Because of this changing of direction, it's very difficult to work with the vector on its own. If we compare this with the acceleration vector, even though there's 2 degrees of freedom, in our setup of these problems where we ignore air resistance, the acceleration vector is actually constant through the entire phase of motion. We notice that it's always pointing down, and this will act as a little bit of a hint for us about how we want to deal with vectors in 2 dimensions to try and make them less complex and make it more straightforward to deal with them. When we want to work with vectors in 2 dimensions, we do some of the same things as we did in the single dimension. Remember, we can choose our origin. So we often choose an origin and consider our horizontal components as x components in the positive and negative direction, and our vertical components as our y components in the up and down direction. We select orthogonal components so that we get a key aspect of 2-dimensional motion. We have 2 sets of coordinates. We just described the Cartesian coordinates, but we could also have polar coordinates. So here we represent our vector with an angular component that measures anti-clockwise from the 0 or the horizontal plane. And we have a radial component, which you can see here is marked as units away from the central origin. This is one of our most common ways of communicating vectors, which means we give a magnitude, the radial component, and a direction, the angular component. So let's consider a vector A with a magnitude of 5 and a direction of 37 degrees above the horizontal. One of the things that's useful about vectors is that set of descriptions. A length of 5 with an angle of 37 means that this vector is the same vector whether it's measured from the origin or it's measured at a random space in the Cartesian plane. So we can use vectors however we want, meaning we can use vectors in either of our coordinate systems. At that same time, we can move a vector to any position, which will let us do a little bit of vector arithmetic. We need to make sure that we understand the common conventions when it comes to coordinates. So in the Cartesian coordinates, we often pick positive directions as up for the y direction and right for the x direction. And note that when we list vector components, we list the x component first and then the y component. In polar coordinates, we always list a positive radial component, so we're always showing the positive magnitude, and the direction is measured anti-clockwise from that positive horizontal position. If you don't use this method of measuring angles, it's going to make some of our calculations later much more complicated because you'll have to reset up your trig ratios every single time. When we worked with vectors in 1 dimension, we first looked at adding and subtracting them visually. And while that's not the method we're always going to use, it helps to give us something to visualize to compare our calculations to later. So let's use the vector that we saw in the previous slide. Remember, that is A with a magnitude of 5, and we're going to be a little bit more precise here with a direction of 36.9 degrees. And let's consider vector B with a magnitude of 2.236 and an angle of 63.4 degrees. We're going to draw these two vectors, and remember, we can draw them wherever we would like on this coordinate grid. So we draw the vector A and we draw the vector B. And then we're going to visually add these together. So that means we're going to move the tail of vector B to the head of vector A. So the tail is the backside of the arrow, the head is the pointy part of the arrow. I'm going to get my little labels out of the way here. Once we've done that, we're going to draw the resultant vector from the tail of A to the head of B. And this will be the vector A plus B. And once we're done drawing in that resultant vector, remember, a vector is a vector anywhere it's drawn, so we can even move that to the origin if we want to use that to find out what the description of this vector is. What if we wanted to subtract our vectors? So this would be the vector A subtract the vector B. To do this, we take the opposite of the second vector. So this would be down and to the left instead of up and to the right. And we get the direction by adding 180 degrees to our original direction, and we don't change the magnitude. And then we repeat the addition steps. So A subtract B, we'll just draw the resultant vector in from the tail of A to the head of B here in dark blue. Notice that it is quite different from the A plus B vector, so it's very important to pay attention to the way you are completing the arithmetic. Now, visually completing this arithmetic is called the tip to tail method. Again, it is simply a sketch, so it's only helpful for visualization because the sketch is too imprecise to try and determine exactly where these final vectors end up. So to work through adding vectors, we have to do them mathematically. So anytime we're given a vector in polar coordinates, we need to complete a process called decomposing the vector. This is breaking it down into its perpendicular coordinates. So we are going to need to add vectors in Cartesian components. Now, to sketch this out, just to give us a better view, we're going to increase the scale. So every box here, instead of being worth 1, is now worth half. And we draw in our vector from the previous slide. So this is a magnitude of 5 and an angle of 36.9. Now to find the horizontal component, so this is the x component, A subscript x, we apply a little bit of our trig ratios. So if you recall, the sine, the cosine, and the tangent ratios all let us compare the sides of a triangle based on an angle. And here we know the magnitude, which is the hypotenuse, and for the x, we want the adjacent side. So we're going to use the cosine angle. So our x component is the magnitude times the cosine of the direction. So we have ax is 5 multiplied by the cos of 36.9 degrees, which is approximately 3.998. For this demonstration, let's just leave this as 4. Let's move on and look at the vertical component. So again, we know an angle and the hypotenuse. Now we want the opposite side of this triangle. So we'll use the magnitude times the sine of the direction. So that gives us the y component of our vector A is 5 multiplied by the sine of 36.9, which is equal to 3.002, and it continues on. And again, for our demonstration, this is approximately 3. Depending on the precision of your angle, it will determine the amount of precision you can have in your sides. We're not overly concerned with those at this point. We'll start to talk about those relationships as we get into application problems. One of the things we do have to be concerned about is that for these equations of A subscript x and A subscript y, this only works when we measure theta from the horizontal positive axis. If you measure theta from any other direction, then you have to reconsider whether or not it's cosine or sine, and that can begin to get very confusing. I often find it's easier to encourage students to just change the angle to being relative to the positive x-axis, which means often when we're working with angles, we are either going to be adding 90, 180, 270, or subtracting 360 from them in order to get a proper angle. The opposite of decomposing a vector into its components is reconciling the components of a vector back into its magnitude and direction. So again, we're going to look at a sketch here. We're going to use that doubled resolution, so each box is equal to half a unit. We're going to consider our vectors from the previous couple of slides. Remember, A is a magnitude of 5 at a direction of 36.9 degrees. B is a magnitude of 2.236 at a direction of 63.4 degrees. So we'll sketch in our two vectors using the tip to tail method, but we'll decompose them using our equations. So recall that the x component of the vector A is 4, and the x component of the vector B is calculated to 1. Then if we consider the y component of vector A, we calculated that as 3 already. Completing the calculations for the y component of vector B, we get that as 2. Here we can sketch in our resultant vector, so this would be A plus B, and we're using that tip to tail method. So from the tail of A to the tip of B, and we can see the Cartesian components of vector A plus B would be the sum of the x components for the x direction and the sum of the y components for the y direction. So we get the vector 4 plus 1 for the x and 3 plus 2 for the y, which gives us the final coordinates of 5 and 5. And for our resultant vector, this would be the Cartesian coordinates of the x component of R and the y component of R. Here we use R as resultant. It often means any vector. So if you were adding these together to get a final position, or if they were velocities to get a final velocity, you would use the corresponding variable. So now that we have the Cartesian components, we reconcile them into the magnitude and direction. So the magnitude of the resultant vector will be the sum of the squares of the two sides. This is just Pythagorean theorem. So we see that our resultant magnitude is 7.0710. We'll round this to 7. And our direction, we'll use the tangent ratio. We've rearranged this to be the tan inverse. And the r component in the y direction will be our opposite side. The r component in the x direction is our adjacent side. So these are both 5. So we find our direction of our resultant vector is 45 degrees. So if we go back to our sketch, that 45 degrees is measured in from the positive x horizontal axis. So our 45 degrees is here. And our magnitude is the length of the black line, so that 7 goes here. So now that we can break two-dimensional vectors up into their components, we can look at how this applies to projectile problems. Conveniently, when we look at motion problems in two directions, the horizontal and vertical components of two-dimensional motion are independent of each other. So any motion in the horizontal direction does not affect the motion in the vertical direction. So we can look at these as separate one-dimensional problems connected together by the object and its time of the scenario. So if we break that vector for velocity into its horizontal and vertical components before, we can see them at every given instant of time for the entire path. And we start to see some very interesting things that we'll look at in the conventions. So now we can start to consider how we're going to solve projectile motion problems in two dimensions. And just like our free fall problems in one dimension, we make some assumptions. First of all, again, this is ballistic motion. So the project's path is defined by its initial velocity. So that initial velocity should have a vertical component and a horizontal component. There'll be no additional inputs during the flight of the object. And at our level that we're studying physics, we'll keep our problems more simplified. We don't have calculus, so we are going to ignore air resistance. This is typically acceptable for small or slow traveling objects. Now we can think of what happens in motion. our horizontal motion. So if we look at the size of the horizontal vector here, we actually see that Vx is constant, which means there is no horizontal acceleration here. And we saw that when we saw the acceleration vector earlier, where it was just a vertical component. Separately, we can think about the vertical or y direction. This is a free fall problem, so we know that we have acceleration is equal to the acceleration due to gravity, which is negative 9.80 meters per second squared down. So that's why we see the vertical component of our velocity vector change in size, shrinking on the way up, growing on the way down, which also tells us that at the max height, we have a vertical component of velocity that's 0. And we notice that that vertical arrow disappears for a split second. And because we're accelerating at the same rate on the way up as we are on the way down, at any point in time here, if we were to sketch a horizontal line across the whole motion, the 2 points that intersect the trajectory would have a consistent magnitude of vertical velocity. As we look at the acceleration vector, we see that described convention. Its magnitude and direction stay constant no matter where the ball is on this trajectory. They always point straight down, meaning there is no horizontal component. The acceleration is entirely vertical. This means when we read problems that we can assume are projectile problems, we can bring this information, the information on this page, to our given systems. Projectile motion problems can present in many different scenarios, and sometimes it's difficult to know we can apply those conventions that we just saw. So it's important to understand that an object is a projectile anytime it enters free fall with an initial velocity component. That initial velocity component can look a little different. So what happens if it has a positive vertical initial velocity? Well, then initially the object is going to travel upwards. It's constantly slowing down due to gravity in that vertical component, not the horizontal. It eventually reaches a max height where its vertical component is 0, and then it begins to accelerate towards impact. Not very evident in this sketch is that the horizontal component of each of these vectors is exactly the same magnitude. What about if it has 0 vertical initial velocity? Well, then initially, the object's at its max height, and that can describe an object that's being held and then dropped, and it can also describe an object that has a vertical component of 0, but a horizontal component with some constant magnitude. And that would be an object rolling off a shelf. And finally, what happens if we begin with a negative vertical initial velocity? Well, this would describe an object that's being held, and instead of being let go, it's being thrown. So it immediately begins with initial velocity and accelerates from there. It also begins at its max height and continuously accelerates towards impact. One of the interesting things about 0 vertical component that you should be able to convince yourself of is that an object that begins with no horizontal velocity and is dropped will hit the ground at the same time as an object that begins with a horizontal component from the same height. And this is going to be really important, and it's going to give us another key fact that we use as we move forward working with projectile problems. So no matter which initial scenario we're given, there could be several different variations of the question we could be asked to solve. There are multiple possible combinations of known and unknown quantities when it comes to these kinematic problems. So 3 of the common things we could look at are, first of all, height. We could be asked to find the vertical displacement of an object. So from the point it starts at, how far up or even down does the object travel? Some of the things that are useful here, because we are often trying to find the max height, we're going to take advantage of one of the assumptions and characteristics of the motion that we can use. If we want to know the object's maximum height, and we're given the initial velocity, and we can assume we know the acceleration, then we'll use our squared velocity equation combined with the fact that the final point in time we're interested in, max height, will have 0 vertical velocity. Remember, the vertical component of motion is separate or independent from the horizontal component of motion, and the only thing that connects them is time. Speaking of time, that's another type of problem we can solve. Time of flight refers to the amount of time the object is in the air, and because our horizontal and vertical components are unconnected, this is entirely dependent on the vertical motion. So we have two types of problems here. The first type of problem is where our total vertical displacement is equal to 0. That means the object takes off from and lands at the same height. In that case, our time up is equal to our amount of time down, which means we can start to use our simple formula. We have a final velocity equal to 0 when we're at max height, and we know our initial velocity and our acceleration, so we can rearrange this, solve for a time. And this will be exactly equal to half of our time of flight, because the amount of time to get to the top will be the same as the amount of time to get to the bottom. What about when our displacement is not equal to 0? So this is times where we want to see an object that lands above or below our initial launch height. In that case, we're going to look to the equation where delta y is equal to the velocity initial multiplied by time plus 1/2 of the acceleration multiplied by time square. And we're going to rearrange that, and I'm going to bring your attention to calling each of these components A, B, and C. And we're going to write that displacement as an addition of the negative displacement rather than subtraction. This is going to help us keep signs straight. Now, why did we call these components that? Well, we're trying to solve for time here, and time shows up in two places in the equation. And one of them is squared and one of them is not. In order to be able to solve this equation, we either have to be very good at factoring or we have to use the quadratic equation. So we can solve for time as time is equal to negative of the b component, which is just velocity initial, plus and minus the square root of that initial velocity squared, subtract 4 multiplied by the a component, which is 1/2 of the acceleration, multiplied by the c component, which is the negative of that vertical displacement. We're going to divide that whole piece by 2 times the a component, which is again 1/2 the acceleration. Doing this will give us two values for when the object is at that height, and those values represent the times that will be at those vertical displacements. The other type of problem we'll see is the range type of problem, and this is asking us what the horizontal displacement is from when the object launches to when it reaches impact. Now, this is tricky because it's going to require the time of flight. And we're going to put an asterisk beside this because this is one of the very few situations where I think it's okay to solve for the time of flight separately, save that value, and then input it into a second equation. And this is because when you solve for time of flight, you usually get 2 responses, and you have to make a decision about which one is most appropriate. One of the other things we're using here is if we want to solve for delta x, we're just going to the definition of velocity. So our horizontal displacement will be dependent on our horizontal velocity and the amount of time we spent flying. And remember, our horizontal velocity is constant without air resistance. All right, I think we're ready to look at our first projectile motion example. So let's consider a volcanic rock ejected from a volcano. So if the rock ejects with an initial velocity of 25 meters per second at a direction of 35 degrees above the horizontal, and the rock impacts the ground 20 meters below its original height, let's find the range of the rock. Your textbook does a couple other examples here, but I figured we should do a novel one. So now that we know what's going on, let's read the problem again to get our given quantities. So we're given an initial velocity of 25 meters per second with a direction of 35 degrees. We have a vertical displacement of negative 20 meters, which is following the conventions we have for our positive x and y direction. And if we're looking for the range, that means we are looking for the horizontal displacement, or the change in x. To calculate range, we're going to look at the delta x is equal to the x velocity multiplied by the amount of time we're flying. And that horizontal component of velocity we can calculate using the magnitude of the velocity and the cosine of the direction. Now, to solve this, we're also going to need to find time, and our vertical displacement is not zero. So this is going to require that quadratic approach. So we set up our equation, delta y is equal to our velocity initial in the y direction multiplied by time. Add that to 1/2 of the acceleration multiplied by time squared. And we're going to rearrange this so that we have it set up in the way that lets us use the quadratic. And at this point, we realize we need to leave ourselves a little bit of room in our given, because one of the assumptions we're making here is that we have a constant horizontal velocity. So acceleration in the horizontal direction is 0, and acceleration in the y direction is acceleration due to gravity, which is negative 9.80 meters per second squared. Now let's apply the quadratic. Remember, the quadratic is t would be equal to negative b plus and minus the square root of b squared minus 4ac, all divided by 2a. And here we substitute our components from our equation. Be very careful about how you use brackets here. So first we get negative of the velocity initial in the y component. We will take plus and minus the square root of, inside of here we have the velocity initial with the y component squared. Subtract from that 4 multiplied by 1/2 of the acceleration in the y direction, multiplied by, be careful about the sign here, negative of the displacement in the y direction. And underneath all of this, we're going to take 2 multiplied by 1/2 of the acceleration in the y component. We're going to input all of the values we know. And as we do that, we have to consider how we're going to enter this in our calculator. So we have negative. We're going to get our vertical component of velocity by taking the magnitude of the velocity, which is VI, multiplied by the sine of the direction, which is 35 degrees. We are going to add and subtract that from the square root, and your calculator is likely going to need an extra bracket here. And again, we introduce that component in the y direction by calculating from the magnitude and the sine of the direction. That gets squared. We're going to subtract from that 4 times 1/2 of negative 9.80 meters per second squared, multiplied by negative of our displacement, which is negative 20. If you're good at algebra, it's okay to do some of the simplification here, like the negative signs will all cancel out in this. So we would have the addition of everything to the left of that subtraction sign. If you want, you can say that the 4 and the 1/2 cancels out to an integer of 2, and this will be a little bit easier to enter into your calculator. And you're going to still have to divide this by, if you would like to cancel the 2 and the 1/2 out in the denominator, negative 9.80 meters per second squared. Don't forget though that you're going to need a set of brackets to keep this whole numerator together. When I calculate these, I enter them all in my calculator, and I do the addition first. So if we do the addition, we end up with a time of negative 1.3103092, and this would be seconds. Now you can scroll back through your calculator and change out that addition sign for the subtraction sign, and that calculation gets us the answer of 3.957719595, and again, seconds. So this tells us that the rock would be at a vertical displacement of negative 20 meters at a time 1 second before the time frame we're considering, that's the negative time value there, and 3.95 seconds after being ejected. It makes more sense to us here to take the 3.95 seconds time frame. One of the tricks for reusing this value accurately is to get comfortable with your calculator's memory function. So when you see me write a letter with a circle around it at the tail end of a number, that's me saying I've stored this in the B memory bank on my calculator. Why do we do that? Well, when we move on to calculate the range, and that's where we go to our equation delta x is equal to the x component of velocity multiplied by the time of travel, which we just calculated, we can plug in the 25 meters per second multiplied by the cosine of 35 degrees. And rather than typing in this long 10-digit number, I can just recall the B memory bank from my calculator. And then my calculator does the calculation, tells me that we get 81.04935243 meters. And looking at significant digits, we're going to say that this is approximately 81 meters, which lets us make the statement, the rock lands approximately 81 meters horizontally away from the volcano. No, this is not a full displacement. This is just a horizontal displacement. So it only looks at how far it's moved in a straight line along the bottom of the image. Let's look at another example that involves working with vectors. We can often have situations where you have multiple velocity inputs, and then we have to try and combine those velocities. Consider a plane flying at 200 meters per second at a direction of 90 degrees, and it experiences a crosswind of 20 meters per second at an angle of 35 degrees. What's the resultant velocity of this plane? Remember, things like wind and current will push objects like planes and boats, changing their velocity. We're going to draw a quick little sketch where we draw in the velocity of the plane, so v subscript p, and the velocity of the wind, which is v subscript w, and then going from the tail of the plane's velocity to the tip of the wind's velocity will give us our resultant velocity. So this is what we're looking for here. Algebraically, that means that the velocity resultant will be equal to the vector addition of the velocity of the plane and the velocity of the wind, which means we need to decompose both of these vectors. So we'll break the plane's velocity down using the magnitude of its velocity and the cosine of the plane's direction for the x component, and the magnitude of the velocity and the sine of the plane's direction for the y component. We'll do the same thing for the wind's vector. Now we can plug in our values, so 200 meters per second times the cosine of 90 for the x component, 200 meters per second times the sine of 90 for the y component of the plane. Now moving on to the wind, we get 20 meters per second times a cosine of 35 degrees for the x component, 20 meters per second multiplied by the sine of 35 degrees for the y component. I'm going to break these down into a more drawn out process here. So recording all of our digits in our calculator, this is a very inefficient way of doing this. We get components of 0 meters per second in the x direction. We get 200 meters per second in the y direction. And we're going to add that to the wind's components of 16 and a bit meters per second in the x direction and 11 and a bit meters per second in the y direction. So combining all of those, we get x and y components of our resultant velocity. So we've decomposed and now added the components. Now we need to reconcile the vector. Remember, we're going to use that Pythagorean type equation, and we're going to also use the tan inverse for the direction component. So plugging the values that we just saw in, we find that we get a magnitude of velocity for our resultant vector of 212 meters per second, and our new direction is now 86 degrees. So the resultant velocity of the plane is approximately 212 meters per second at an angle of 86 degrees. So one of the tricky parts of working with two-dimension quantities is the fact that you need to decompose and reconcile vectors. I think our examples have made us more comfortable with that. We can't forget that we still have to think of things with the context of our kinematic concepts. So the quantities we have considered dimensionally, we also have to consider their definitions. So don't forget that when we think about kinematics, we look at displacement, velocity, and acceleration. The displacement, remember, its definition is change in position. Positions are often given in Cartesian coordinates. So if we have an orange and a purple spot, they would have their own x and y components each. And that displacement, which we often represent with a delta x, gives us a little bit of risk for confusion here. So that change in position has to be considered, that there will be a x component of the change in position and a y component in the change of position, which means we have to look at our full calculation here. To get the full vector quantity of displacement, we have to get the magnitude, which will be the difference between the purple and orange x components squared, added to the difference of the purple and orange y components squared. We take the square root of that whole result, and that gives us the magnitude of displacement. To get the direction of that displacement, we also have to use the tan inverse of those two differences. Be very careful when you're working with problems. Remember, the difference in the purple and orange x components is written out as delta x sometimes. So when we talk about displacement, often we'll see that in 2 dimensions, we represent displacement with delta and some other symbol. Sometimes it's r, sometimes it's s. When we think of velocity in 2 dimensions, we go back to its definition. And remember, it's change in position over change in time, or displacement over change in time. So if we take that same displacement vector from the previous question, and we think about our velocity equation, velocity is equal to displacement over time, we have to understand that time is a scalar quantity. So it affects magnitude only and not direction. So if we're trying to calculate the velocity of an object, we have to do the same calculation that we just did for the magnitude and divide that by the change in time, but we have no difference for the direction. My change in position and my velocity will have the same direction. Acceleration can be the most difficult of the 2-dimensional things to calculate. So change in velocity over change in time, we have to consider the vector subtraction of the 2 velocities. So if we consider an object that has an initial velocity up and to the right and a final velocity that is horizontal, think of our acceleration definition, change in velocity over change in time. We calculate this with the final velocity subtract the initial velocity divided by change in time. So we need to be very careful. Often students will sketch the problem exactly as I have here. Show the velocity that we initially have and then the velocity that we end with. When we consider the vector addition of these 2 quantities, it's actually going to look more like this. So we have to consider final velocity, then we have to take the opposite of the initial velocity, which will be the flipped over version of the initial velocity, and we'll have the tip to tail method show us that the acceleration is actually down and to the left here. So to calculate this, we have to decompose both vectors using our Vx will be the magnitude of velocity times the cosine of its direction, and the Vy will be the magnitude of the velocity times the sine of its direction. And we have to do those decompositions for both final and initial velocities. Then we have to reconcile all those components. So to get the magnitude of the change in velocity, we take the square of the change in the x component and the square of the change in the y component, which means we have to calculate the change in the x component using our decomposed values. And we also have to reconcile our direction, and that'll be the tan inverse of the change in the y component over the change in the x component. Remembering, you have to do them with the decomposed values. So you can see that acceleration often becomes the most tricky because 1, there's a conceptual issue for the way we draw things, and 2, the calculations are large. So you have to make sure you have lots of room to complete them. Let's go back to our plane and let's consider if the plane experienced that crosswind for a duration of 2 seconds. And let's determine what the acceleration would be. So if we have our sketch from before, remember we had the 2 velocities and we calculated the resultant velocity. So this is our final velocity, and the plane's velocity at the start, the dark blue line, that's our initial velocity. So if you think back to how we calculated this, we had our resultant velocity was the sum of the plane and the wind. So if we substitute what we just said, that means our final velocity is equal to the initial velocity plus the velocity of the wind. And if we rearrange this one, that means that the velocity of the wind is the difference between the final velocity and initial velocity, which is very convenient because that's our vector definition of our change in velocity. So if we want to calculate acceleration here, that means we have change in velocity over change in time, which is just equal to the velocity of the wind over change in time. And completing this calculation, we would get 20 meters per second at a direction of 35 degrees, all over top of 2 seconds. Remembering that time affects magnitude and not direction, that means we see that we get a 10 meters per second squared acceleration at an angle of 35 degrees. So the acceleration is 10 meters per second squared in the direction of 35 degrees from the positive horizontal. I like this example because it reminds students to think carefully about the definition of our kinematic quantities. We were able to solve this problem a little bit more quickly because of the access we had to delta V. But we need to remember, in most problems, we can't just do this simple rearrangement of the two quantities. We will actually have to do the entire decomposition and reconciling of the vectors. The only reason we could skip that this time is we had already done some of the decomposition work in a previous example. Speaking of previous example, let's look at what two-dimension displacement is, and let's look at our volcanic example from earlier. So what was the vector displacement of that volcanic rock? Well, first of all, remember, we calculated the horizontal displacement, and that gave us a delta x in full resolution of 81.04935243 meters. I'm going to store this in my calculator as value c. And we also had a time elapsed of 3.957719595 seconds. Again, let's store that in the calculator in memory bank D. So if we want to look at vector displacement, we're looking at the displacement from our initial position to our final position. So you'll notice that this line does not lie in either of our horizontal or vertical planes. So this means we have to do our decomposition and reconciling of our vector components. Because this doesn't match x or y, we'll use that notation we talked about earlier. We'll call this displacement our delta r as a vector. So our displacement will be equal to our final position, r subscript f, subtract our initial position, r subscript I. Let's make this problem a little more simple. Let's take r subscript I as 0. We can define that position on our chart, which means we have a horizontal or an x component of 81 that we stored before, and we have a vertical or a y component of -20 meters. So if we want to find our vector displacement, we need to reconcile the magnitude and the direction. So the magnitude we can calculate by recalling that value c and squaring it, and adding to that the square of our -20 vertical displacement. And to do our direction component, we'll take the tan inverse of -20 divided by that value we've stored in c. It's very important to use the -20 here, otherwise you're not going to get the correct angle. When we do our calculations, we find that we get a magnitude of displacement of 83.48052.186 meters. I'm going to store that in my calculator as well. At a direction of -13.861, you know what, it's approximately 13.9 degrees. The negative means that it's below the horizontal, which matches our sketch. While we're at it, why don't we consider the average vector velocity? So remember, velocity average is calculated by taking our displacement and dividing it by our time. So that's the information we have here. We're not considering how the rock moved, we're just considering those two positions. That's what makes it an average. Conveniently, we've stored these values in our calculator, so we'll recall E and we'll divide that by our recall D. And we see that we get an average velocity of approximately 21.09308. We've got a lot of information there, meters per second. This is the magnitude. What direction will it be in? Well, it will share the direction of our displacement because the time function in velocity calculation doesn't affect the direction. So what can we say? We can say that the rock has a displacement of approximately 83 meters and an average velocity of approximately 21 meters per second. Both of these quantities occurring at an angle of approximately 13.9 degrees below its initial positive horizontal. If you want to break this velocity component back out into its horizontal and vertical directions, be very careful in how you use that angle. Some calculators will not let you use a negative angle in these calculations. In that case, you'll have to convert it by adding 360 degrees. So there we have it. In this lecture, we extended our kinematic concepts from one dimension to two dimensions, which means we had to introduce the concept of using vectors in their two-dimensional components. And we explored steps for applying vector addition and subtraction to problems, which allowed us to investigate all the nuances of projectile motion And this will be no different than the way we consider all two-dimensional kinematic quantities. The only difference between our thinking of a plane and our thinking of projectiles is that in projectiles we begin to introduce some additional assumptions. Other than that, when we work in two dimensions, we do everything the same.